So let us look at how to go about this problem. So we have here initially the specific volume. Let's call the initial state as say 1, and then we have the final state as 2. So we have some kind of a piston cylinder arrangement. So we draw it like this. So our system is the gas included in the piston cylinder arrangement. So it's given here that the mass of air is 1 kg. So we are having a fixed mass, which is why we are going to deal with this as a system. So the mass initially and finally is both 1 kg. The specific volume initially, we will call it as V1, is 0.2 meter cube per kg, and the temperature initially is 580 Kelvin. What it says is, it is expanded from 0.2 meter cube per kg and 580 Kelvin to 0.8 meter cube per kg. That's our final volume, and a final temperature T2 of 290 Kelvin. So we have the initial state completely, we have the final state which is also there, and we are told that the expansion process follows this kind of an expression. We have the final temperature as well. We are asked to find out the heat and work interactions. We are given that the process follows PV to the power 1.5 is 0.75, and we are also given the value of CV, which is 0.718 kilojoule per kg Kelvin. So there is a gas over here which is undergoing some process. In this case, the volume is changing from 0.2 to 0.8. So the volume is increasing, the specific volume is also increasing. So we would call this kind of a process as expansion. So we know that this is following the process. PV to the power 1.5 is 0.75. 0.75 is a constant. So this follows PV to the power 1.5 is constant. So the general expression for that kind of thing is what we said, PV to the power n equal to constant, what we call as a polytropic process. So here of course we have PV to the power 1.5 is 0.75. We can consider this to be a simple compressible system. There is expansion of the gas, there are no other effects, there is no electric or magnetic work, there is no shaft work and so on. So there is only displacement work because of the displacement of the piston from some initial position to some other final position. So our initial volume is this, our final volume is all the way up to here where the piston has moved out. So this is the position of the piston initially, this is the position of the piston finally. So we know that we can get the work which is essentially of the form of PdV. So the work would be integral of PdV. So if we are using specific volumes, we can also write this as integral of P into mass into specific volume, and we can write that as integral. Mass is constant because it is not changing. Sorry, this should be d of mv. So volume is mass into specific volume. Mass is not changing, mass is a constant, therefore this is 0. So essentially dV is mdV. So we have taken the m outside, it's a constant, so we have this expression. We have integrated this earlier, but we can integrate it again as well. This is from 1 to 2. So in order to integrate, we need to write we have two variables p and v. We need to convert this into single variable. M is a constant, it's not a problem. So it's integral 1 to 2. We can eliminate p from this. So p is essentially 0.75 by v to the power 1.5. So the integral for this is like v to the power n. So the integral of that would be, this is v to the power minus n actually. So minus n plus 1 by minus n plus 1. So essentially we would get this is our integral. So over here this part is known, this part is known. The question says that the mass is 1 kilogram. So this is also known. So we need to know these values. We know the value of V1, we know the value of V2. What we do not know is P1 and P2. So we know V1, we know V2. What we do not know is P1 and P2. But what we know is that this holds between any 2 points 1 and 2. That's also known. What we also know is the temperatures. So what we can write is P1 V1 to the power 1.5 is equal to constant, that's 0.75, is equal to P2 V2 to the power 1.5. So we know V1, we know this, so we can find out P1 from here. So P1 is 0.75 by V1 to the power of 1.5. V1 was given as I think 0.2 and 0.8 meter cube. Similarly, using this part of this expression, P2 is 0.75 divided by this. I believe this is about 8.38 bar. And this is about 1.04 bar. Let me just check P1 again. I think that's correct. Okay, I think I did not write this. Yeah, I did not write this correctly. So how do I erase? Yeah, when I integrated it, I made a mistake in the formula over there. So this was V power So, when you integrate this, we have done this integration earlier. So, it is of the form, I will leave this all out as a constant. So, we have some constant m into some constant dv by v power some n. So, this is like v power minus n plus 1 divided by minus n plus 1 between state 1 and 2 into the constant into m. So, this constant is equal to P1 V1 power 1.5 is equal to P2 V2 power 1.5. So, if you substitute that, then you get this expression in this form, not what I had written earlier. So, we have the values of P1 and P2 over here. So, what we need is to now substitute it here. So, this is 1 W2. So, we have 1 W2 is 0.75 into 1. I am going to now convert it into SI units. This is a bar. So, this is in 10 power 5 Pascal. This is 1 kg. V1 is, I had it here, 0.2 whole divided by 1.5 minus 1, which is essentially 0.5. So, I have 8.38 into 0.2 minus 1.04 into 0.8. So, I have about 0.422 into 10 to the power 5 into 0.75, which I haven't yet multiplied. So, that is 0.316 in 10 power 5. So, I am going to write it as 31.6 into 10 power 3 joule, or 31.6 kilojoule, which is the work interaction for this process. So, we were asked to find out the work interaction, which we have done. We are also asked to find out the heat interaction. So, what I am going to do is, we are using the first law of thermodynamics for this problem. So, what we can do is write down the first law. We had written it in various forms, maybe I will write it in this form. For a system undergoing a process, we have it like this. In this case, the system itself is stationary, so there is no change in the potential energy of the system. There is also no change in the kinetic energy of the system because it is not moving. So, this E, which is usually expanded as internal energy plus kinetic energy plus potential energy, if we were to differentiate that, we would get dE is du since there is no change in kinetic energy, this is 0, there is no change in potential energy, this is 0. Therefore, I can replace dE by du. So, I get this expression. I know the value of work done, which we have just calculated. I want to find out the value of heat, which I did not know, and here I have du. So, du can be written as m into Cv into dt, assuming that what we have is an ideal gas. So, I can write this as del q minus del w, or del q, which is what I am interested in, is m Cv dt plus del w, or 1 q2 is m into Cv integral of dt from 1 to 2 is essentially delta t 1 to 2. Right, that is T2 minus T1. So, I am going to write it like this. So, I have the mass which is 1 kg, I have Cv which was I think given as 0.718 kilojoule per kg Kelvin. So, I am going to write in SI units as 718 joule per kg Kelvin. This is a small k in case that is not clear, into delta T is, I think the final temperature was 290 Kelvin, the initial temperature is 580. It disappeared somewhere. Plus 1 W2, which we just calculated as 31.65 in 10 power 3. Where all of these are now in joules. So, I can find out this. So, this is a negative term and this is a positive term. So, we can find out what the values are. So, I have 718 . So, this is minus 208 kilojoule plus 31.65 kilojoule. Which tells us the value of this. So, by the convention which we had, we said that work going out of the system is positive, heat going into the system is positive. So, that is our general convention for any system. Heat coming in is positive, heat going out is positive. So, here we see that in this case the work was positive, which means the piston is moving out and it is expanding. The heat is negative, which means that heat is also going out of this system. So, this is essentially the heat lost has a magnitude of 176.3 kilojoule. The heat interaction is negative for the system, which means the system is losing heat. So, the system is doing work as well as losing heat due to changes in internal energy. So, that is what we see. So, initially this was the temperature of the system. Initially it had a high temperature, it had a lot of energy. Finally, this is the temperature, it has a lower amount of energy. So, the system is losing energy by both doing work and by giving out heat. So, the first law of course is the conservation of energy. Often there are various ways of looking at it. Often one of the ways or one of the thoughts given in textbooks is like, for example, you have a bank account, you can put money into it, you can take money out of it. You can put money into it by going and depositing cash. You can also put money into it by doing a bank transfer. Similarly, you can take money out of it by, for example, using a debit card, or you can go and take cash out. So, you can think of one of them as say heat, one of them as say work. So, the net when you deposit in is to increase the balance inside the bank account, which is to increase the energy which is there in the system. If you withdraw things from it, the energy reduces. You can withdraw either in the form of a check or cash or a debit card. So, you can withdraw either in this case in terms of either work or in terms of heat. So, that is essentially what we see.